Hi there. Today's lecture we're going to talk about work. So in the previous lecture we talked about energy and we discussed many different types of energy. So we talked about kinetic energy, gravitational potential energy, elastic potential energy. And within the system we learned that energy can be transformed from one form to another as long as the system is not interacting with the environment. The total energy of the system is unchanged. Okay, so if there's no external forces acting on the system, then we can say that the total energy initial equals the total energy final. But oftentimes systems do interact with their environment, and so there is a change of energy of the system, so we can no longer say that the total energy initially equals the total energy final. Sometimes energy is added or energy is removed from the system. And so in this case, interactions with the environment transfer energy into or out of the system. So anytime an external force is acting on a system, we say that work is done. Okay, so for example, if we apply a force on an object, or if there's friction, if there's tension, these are all cases where external forces act on a system, causing work to be done on the system. When the force acts in the direction of the motion, it causes the particle to speed up or accelerate. Then we say the work done is positive. So it increases the energy of the system. So we're adding energy to the system. When the force opposes the motion, then it causes the object to slow down. And then we would say that the work done is negative. So this results in a decrease in the total energy of the system. If the force does not affect the speed of the object at all, or if the particle is not even moving, then there's no work. To calculate the work done, you can multiply the component of the force that's acting on an object in the direction of motion by its displacement. And to find the component of the force, you end up just multiplying it by cos of the angle. Now here I'm calling the angle beta, okay, because I don't want to confuse it with the angle of the incline. So here's my formula below. My work is equal to the force. So this is the external force that's acting. And we'll see this in use, so it'll make more sense. So this is the external force acting on the object or on the system. My delta S is my displacement. And then cos beta, where beta is the angle between the force and the displacement. Okay, so these two are vectors. It's the angle between those two vectors. So let's see what we mean. Here's a little picture. Okay, so my object is moving in this direction and this is the distance. So this is like my delta S here. They're just calling it delta R. It's the same thing. This is my force. So here's one case. So they're showing two different examples, but this is my force acting on my object. Okay, so this is my object over here. And it's moving in this direction, the direction of delta R. Okay, so it's moving in that direction, and the force is helping it to move in that direction because it does have a component that is parallel to the direction that it's moving, right? So this, they call it F sub S, so it's just saying that it's the component of that force that's parallel to the direction that it's moving, and beta is the angle between the force vector and the displacement vector. Okay, the displacement vector is this vector over here, the blue vector. Okay, so let's do some questions here where we can use work to explore it further. So a strap is inclined upward at a 45-degree angle, pulls a suitcase 100 meters through the airport. Okay, so this is like my suitcase right here. And there's a strap on the suitcase. So it's like a rope and it's pulling on the suitcase. Okay, it's angled upward at an angle of 45 degrees. So this angle here is 45 degrees. And it pulls the suitcase 100 meters. So this is my delta S. Okay, that's my displacement through the airport. The tension in the strap, so this is my tension, is 20 newtons. How much work does the tension force do on the suitcase? So the work, and I can put a little subscript, the work done by the tension is equal to the force of tension times the displacement times cos of beta, where beta is the angle between the force and the displacement. Okay, so which way is the object actually moving? My displacement is going this way. So this is my delta S. Okay, so when I'm looking for my work done by tension, it would equal my force of tension, which is this, 20 newtons, times my displacement. So my displacement was 100 meters. So times 100, cos of the angle between my displacement and my force. So that would be 45 degrees. And so now I'm just going to type this on my calculator. 20 times 100 times cos of 45, and I get 1414, and my units would be joules. Okay, so work is the energy that you're adding to the system or you're removing from the system. We see that this is positive work because this tension is helping it move in the direction that it's actually moving, so it's making it move faster. So that's why it's positive. Okay, let's do question 2. An 8 kilogram crate is pulled 5 meters up a 30-degree incline by a rope angled 18 degrees above the incline. Okay, so here's my incline, and it's at a 30-degree angle. And I've got this crate here, which is 8 kilograms, and it's being pulled up the incline by a rope. So again, there's going to be a force of tension acting on it, and that tension is acting at a 18-degree angle above the incline. And the tension, they tell us, is 120 newtons. And the crate's coefficient of kinetic friction is 0.25. So it's asking us to find the work done by tension, by gravity, by the normal, by friction. Okay, so we're trying to find the work done by all these things. And remember, we said that the equation for work is equal to the force times the displacement times cos of the angle between the force and displacement. So when we do the work done by tension, we would find the force of tension times the displacement times cos of the angle between the force of tension and the displacement. When we do the work done by gravity, we would be putting in the force of gravity times the displacement times cos of the angle between the force of gravity and the displacement. So before we continue, let's draw a free body diagram so that we can find all of these values of the forces. So this dot here is our crate. So what forces are acting? We have the tension already. We also know that there's a force of gravity, and Fg equals mg, and the mass is 8 kilograms. So it's 8 times 9.81, and I'll just type that up, 8 times 9.81, and I get 78.48 newtons. Okay, I also have a normal force, and the normal force is perpendicular to my surface. So that's my normal force. So I would want to decompose my force of gravity into x and y components. So it looks like this. So this would be my Fgy perpendicular to the ramp, and this is my Fgx parallel to the ramp. And this over here is going to be 30 degrees, just like the angle down here at the bottom. So on the side, let's solve for Fgx and Fgy. So Fgx is opposite to the 30-degree angle, so it's going to equal 78.48, which is my hypotenuse, sine of 30 degrees. Since it's opposite, we're using sine. I'm going to type that up, 78.48 times sine of 30, and I get 39.24 newtons. And Fgy is equal to 78.48. The y is the adjacent side to the 30 degrees, so we're going to use cos of 30. So I get 78.48 cos 30, which is 67.97. Okay. Also, my tension, I'm going to want to decompose it into x and y components, so I'm going to find that as well because my tension is also on an angle from my ramp. So this would be my tension x, and this one would be my tension y. So let's find that next. So my tension x we see that there's an 18-degree angle there. Tension in the x direction would be the adjacent side to that. So it would be my hypotenuse, which is 120. Since it's adjacent, we're going to use cos of the angle, which is 18 degrees. So 120 cos 18, and that gives us 114.13 newtons. And my tension Y is opposite of the 18 degrees, so it's going to be 120 sine, since it's opposite of 18. And that gives me 37.08 newtons. Okay, so now I know all of my forces so far that have x and y components. The normal force is the one that I'm going to figure out next. And because I know that this object is moving up the ramp, it's only moving in this direction here, which we'll say is the x direction. It's not moving in the y direction at all, so that means it can't be accelerating in the y direction at all. So if I were to say that the y direction this way is the positive direction, I would say F net in the y direction is equal to mass times acceleration in the y direction. But we know that the object's not moving in the y direction, so it's also not accelerating in that direction, because acceleration means how fast is its speed changing. But it's not moving at all in that direction, so its speed's not changing in that direction. So the acceleration in the y is 0, and mass times 0 is still going to be 0. So now we're going to write out all of our forces that have y components. So we have the normal force, which is acting in the positive y direction. So that's going to be F normal. We have the tension in the y direction. So that's positive. And then we have FGY, which is going in the negative direction. So it'd be minus FGY. Those are the only forces that have y components. So all of those put together have to equal 0. So I can rearrange to solve for F normal, and I get FGY minus Ty. And I know what my values are. I did them on the side. FGY we said was 67.97 minus Ty, which is 37.08. And I'll type that up. And I get 30.89. So now I know my F normal. The question also told me that there's friction in this question. Okay, they tell me the coefficient of friction. We know we're moving up the ramp, so the friction, the force of friction, must be pointing down the ramp. And since the object is moving, we would say that this is the force of kinetic friction because it's in motion. So force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. The coefficient of kinetic friction was given to us, 0.25, times the normal force, which we just found was 30.89. And when we multiply those, we get 7.72 newtons. Okay, so now I know what all my forces are on my free body diagram. So now we can go ahead and start answering the question. So let's start with, I'm going to rewrite this on the side. Okay, let's start with A. So again, the work equation is equal to force times displacement times cos of the angle between the force and the displacement. So A is asking what is the work, or how much work is done by tension. So I'm going to put a little t here to say this is the work done by tension is equal to the force of tension times the displacement times cos beta. And they tell me in the question that the crate is being pulled 5 meters. So in every single case, our displacement is 5 meters. Okay, so that's what we're using for our displacement. So work done by tension is equal to the force of tension, which we found earlier, or which they told us in the question is 120 newtons. 120 times the displacement, which we said was 5, times cos of the angle between the force of tension and the displacement. So the displacement, it's going this way. We're moving up the ramp, and the force of tension is this over here. So the angle between those is this 18 degrees. Okay, so this is cos of 18 degrees. All right. So what do we get here? I'm just going to type this on my calculator. 120 times 5 cos 18. and I get 570.6 or 571. This is work is always in joules, just like energy. Work means how much energy are you adding to the system. Tension, work done by tension is positive. That means the tension is helping the object move in the direction it's moving. So it's making it speed up. And that makes sense because this tension here is pulling the object up the ramp. And that's the way it's moving. Okay, for B, it says how much work is done by gravity. So we're going to write work done by gravity is equal to the force of gravity times the displacement times cos of the angle between the force of gravity and the displacement. So let's look at that. So our force of gravity is this vector over here, and the direction that we're moving is up the ramp like this. Okay, so what is the angle between those two vectors? It would be this angle, this full angle here. Okay, so we've got this smaller angle here, which is 30, and then this other angle over here, which is 90. So 30 plus 90 is 120. So the beta in this case is 120 degrees. So let's fill in everything that we know. FG, which is 78.48, times delta S, which is always 5 meters in this question, times cos of the angle between the force of gravity and the displacement, which we said was 90 plus 30, or 120. Okay, so it's this full angle right here. Okay, so now I can just type this on my calculator. 78.48 times 5 times cos of 120, and we'll see we get a negative answer, negative 196 joules. So it's negative because the force of gravity is not making it speed up as it moves up the ramp. It's slowing it down, so it's making it harder for it to move up the ramp. Okay, so that's why the work done by gravity is negative in this case. Okay, C. Work done by the normal force. So work done by the normal is equal to the force of the normal force, so it's the normal force, times the displacement, times cos of the angle between the normal force and the displacement. So we found out that the normal force is here, 30.89. The displacement is 5 meters. Cos of the angle between the normal force and the displacement. Okay, so what's that angle? The normal force is over here, pointing this direction, and the displacement is going this way. This is the direction that it's actually moving. So what's the angle between those two vectors? 90 degrees. Okay, so this should be cos of 90. And what is cos of 90? So if you think of the cos graph, or if you even just type it into your calculator, cos of 90 is 0. So this whole thing becomes 0 times anything is still 0. So 0 joules. So that should make sense because the normal force is perpendicular to the surface. It's not helping the object move up the ramp. It's not helping it move down the ramp. It's not really influencing how fast it moves at all, okay? Because it's perpendicular to the surface. So it's not making it go faster or slower. It's not really doing anything. So that's why the work done by the normal force is 0. Okay. D, how much work is done by friction? So I'll write that. Work done by friction is equal to the force of friction. So here I'll write force of kinetic friction times the displacement times cos of the angle between the force and the displacement. Okay, so what is the force of kinetic friction? We found it out, 7.72 times the displacement, still 5, times cos of the angle between the force of friction and the displacement. Okay, well the force of friction is going this way, and the object is moving up the ramp, so the displacement's going this way. So the angle between those two vectors is that full line, so it would be 180 degrees. Okay, so I'll type that up, 7.72 times 5 times cos of 180. Well, cos of 180 is just negative 1, so my answer just ends up being negative 38.6 joules. And that makes sense because friction is not helping it move up the ramp. Friction is opposing the motion, so friction's slowing down. That's why the work done by friction will always be a negative number. Okay, part E. What is the increase of thermal energy of the crate and the incline? Okay, so the thermal energy is always equal to the work done by friction, except it's positive instead of negative. So the work done by friction is a negative value because it makes the object slow down. Now that amount of work, because it's negative, it means that 38.6 joules of energy was lost. So it wasn't added to the system, it was removed from the system, it was lost. And how does it get removed? What does it look like? So remember we talked about how energy cannot be created or destroyed, it can just be transferred from one form to another. So this form of energy that gets lost is just transferred into thermal energy or heat. So the increase of thermal energy is just the same number, so I'll put it in here, 38.6 joules of thermal energy. Okay, so that's the increase of thermal energy of the crate and the incline. So basically the crate itself and the incline below it, the surface below it, are getting heated up because friction is like the two objects are rubbing against each other, causing friction, making everything heat up, and that's producing thermal energy or just heat. Okay, so the work done by friction will be negative. The amount of thermal energy that was produced will be the positive value of the work done by friction. Okay, so when there's an external force, such as an applied force, a force of friction, or a tension that's acting on the system, work is always going to be done. And therefore, the energy that's added to or removed from the system. Okay, so there's always energy added to or removed from the system anytime work is done. In this case, we can no longer say that the total energy initial equals the total energy final. We must also include this one term here. The total energy we have initially plus the extra energy that's added to the system, which is called the work, is equal to the total energy final at the end. Okay, sometimes that work will be a negative, and that's okay. We always just keep it on the left side of the equation, so we add it to the total energy initial to find out the total energy final. Okay, so it could be a positive or a negative value. So let's see how that works. Question 3. So in the figure below, we have a 900 kilogram crate on a rough surface inclined at 30 degrees. So I'll just write in here, this is 900 kilograms. A constant external force, which they call P, and it equals 7,200 newtons, is applied horizontally to the crate. While this force pushes the crate a distance of 3 meters up the incline, okay, so this is our delta S. This is the distance or displacement that it travels. Its velocity changes from 1.2 meters per second, so V1 is 1.2 meters per second, to 2.3 meters per second. How much work does friction do during this process? Okay, so we have energy when it's down at its lowest position over here, and we have energy when it's at its higher position over here. But there's a difference in the energy, and that's because work was done to the system, and the work is done by this force over here that's applied. So let's add our equation that we'll start off with. So the total energy initially plus the work done by the system, I can write work total, is equal to the total energy final. So initially, what kind of energy do we have? So we can say that our reference position right here is 0. So this is where I will just draw a little triangle over here. And I'll say my delta, or I'll say my H initial over here is 0 meters. And so then how do we figure out what our H final is over here? Well, we can look at this triangle. We know that this is 3 meters. We know that this is 30 degrees, and we can use SOHCAHTOA to solve for this value over here, which would give us the H final. So that is the opposite side of the 30 degrees. So if we did 3 sine, since we're looking for opposite, of 30, I'll type that up. So 3 sine 30, and I get 1.5 meters. So my H initial is 0 because we're saying that's our reference position, and at the top our H final is 1.5 meters. Okay. So now we're going to think about, well, what types of other energy do we have in the equation? in the system. So let me just clean this up for a second. Okay. All right, so initially we talked about 3 different types of energy before. We have gravitational potential energy, kinetic energy, and elastic potential. Now in this question, there's no spring at all involved, so I'm not even going to include elastic potential energy. I'll include kinetic energy, and I'll include gravitational potential energy. The work, there's only one external force acting on the system, and that's this force here that they called P. So I'm going to call this work done by P is equal to the 2 different types of energy, kinetic final plus gravitational potential final. Again, I'm not including elastic potential because there's no spring involved in the question at all. So initially and final, there is a speed that the crate's moving. So we will have kinetic energy in both cases. Gravitational potential, initially we set that height as the reference height where the height is 0. So gravitational potential energy initially would just be 0. But at the end, UG final would have a height, so that gravitational potential energy would not be 0. Okay, so now we can go ahead and substitute our value or our equations in. So EK initial, that would be 1/2 mv initial squared. Work done by this force called P. The equation for work, I'll write it up here. Work is equal to force times displacement times cos of the angle between the force and displacement. So instead of calling it F for force, I'm going to call it P because that's what they called the force in the question. P delta S cos beta equals EK final, which is 1/2 mv final squared, plus UGF, which is mgh final. Okay, so what is it that we're looking for? How much work does friction do during this process? So we're looking for the work done by friction. So in fact, we don't really need to know what this value is or this value or this value. We're really just looking for, it wants the work done by friction, not the work done by P. So that means there's another work term in this equation that we missed. So let me clean this up. Okay, so what do I mean? So in the question, we wrote this equation, E total initial plus work total equals E total final. If there's only one external force acting on the system, then the work done by that force is what we would put here. So in this case, work done by P, the force that they called P. But the question says how much work is done by friction. So that means there must be another force, which is the force of friction. So where's that force of friction in our picture here? So we have this force P acting on the system, or on this block here, the crate. And now there's also friction because the question mentions friction in it. So the object is moving up the ramp, so friction would be going in the opposite direction. It would be coming down the ramp. So this is the force of kinetic friction. And we're looking to find the work done by that. Okay, so the total work in the question, we have to include all the external forces. So we're including the work done by this force called P, plus we're including the work done by friction, equals E total final, which again was EK final plus UG final. Okay, so we're solving for this work done by friction. So I'm not going to rewrite it as friction, like the force of friction times displacement times cos of beta, because we're not looking for one of those individual components. We're looking to solve for work done by friction. So I'm leaving it just like that. Then I'm going to go ahead and put in my equations again. V final squared plus mgh final. Okay, so the goal of this question is to find how much work does friction do. So that means this right here. So that's what I'm trying to solve for. So I can just rearrange right now if I'd like. I can say the work done by friction is equal to, I'm just going to rearrange everything. So everything on the right is staying on the right. 1/2 mv final squared plus mgh final. And then I'm going to bring everything over from the left. So it's minus 1/2 mv initial squared minus P, that's the force that they told us is 7,200, delta S cos of the angle between the force and the displacement. So now I can sub everything in. 1/2 My mass is 900 kilograms. My V final is this 2.3 meters per second over here, squared, plus M is still 900, G is 9.81, H final we said over here is 1.5, minus 1/2, M, which is still 900, V initial, which is here, 1.2 meters per second squared, minus, so now we have P, which is that force they told us was 7,200 newtons, times delta S. So the question tells us it's moving 3 meters along the ramp, so that's 3 cos of the angle between P and delta S. So let's look at our picture for that. So P is going in this direction and delta S is going in this direction. So in order to know the angle between two vectors, we need them to be tail to tail. So I'm going to slide my P vector over here. So this is now my P vector and this is my delta S vector. So what's the angle between those two? It would be this angle here, 30 degrees. Okay, so that's my beta for this question. So I'm going to just put in 30 degrees here. And that's it. I'm just going to plug everything into my calculator and solve for W final. So 1/2 times 900 times 2.3 squared plus 900 times 9.81 times 1.5 minus 1/2 times 900 times 1.2 squared minus 7,200 times 3 cos 30 equals negative 3730 joules. All right, so notice the work done by friction is a negative value. That's because friction, which is pointing down the ramp, is making it harder for the crate to move up the ramp. Okay, so it's opposing the motion. It's making it harder to push the crate up the ramp. All right, so that's question 3. Question 4. In the figure, a block of mass M is moving along the horizontal frictionless surface with a speed of 5.7 meters per second. If the slope is 11 degrees and the coefficient of kinetic friction between the block and the incline is 0.260. So it's saying that this is the only spot that has friction. Okay, only when it's along this slope here. So the coefficient of kinetic friction here is 0.260. How far does the block travel up the incline? Okay, so eventually it comes to a complete stop. All right, so let's write out a formula. So initially, the total energy we have plus the work done on the system by external forces is equal to the total energy final. There's no spring in the question, so I'm just going to include kinetic energy initial plus gravitational potential initial plus the work done by the system. Well, the only external force that's acting here is friction. Anytime there's friction in the question, that will be an external force that's acting. So I'm going to write the work done by friction is equal to the total energy final, which again will say kinetic final and gravitational potential final. So out of all the different types of energy, which ones will be 0? So initially, this is our V initial, is 5.7 meters per second. So since there is an initial speed, then there will be kinetic energy initially. We'll say when we're at the bottom of the ramp here, so like this height over here is where the height is 0. So initially then it doesn't have a height at all. So this whole UG initial would be 0. And at the end it will have a height. So whatever this is here, this will be our height. Okay, so we don't know what it is, but we do know that it will not be 0. So we will have a UG final. But it does say how far will it travel up the incline. So we're assuming it's going to come to a stop at some point, and that's when it reaches its highest point. So when it gets to the highest point, the speed, so the final speed would be 0. Okay, so then that means that EK final would be 0. So now our equation is a little bit different. So we'll put in all the formulas. EK initial is 1/2 mv initial squared. Work done by friction is equal to the force of friction, kinetic friction, times the displacement, times cos of the angle between the force and the displacement, is equal to UG final, which is mgh final. Okay, so delta S is referring to the distance or the displacement traveled by this block while it's experiencing this force. So in this case, the force of friction. Now there's only friction between the block and the incline. So this is the only position along here that we are using to calculate delta S. So delta S is just this distance here. Okay, the question is asking how far does it travel up the incline? So you have to be really careful when you're reading the questions, because sometimes it will ask how far does it travel up the incline, like this one, but sometimes it will ask what height does it reach up the incline. So this would be the height up the incline. Okay, so in this case we're looking for the delta S. Delta S is what we're trying to solve for. Okay, so if we're trying to solve for delta S, we want to keep delta S over here, but the H final that's over here, we're going to want to substitute it out so that it's in terms of delta S instead. So if we redraw this triangle over here, and this is 11 degrees, and this is delta S, and this is H, then what's a relationship that relates delta S to H? So we can use SOHCAHTOA since it's a right angle triangle. H is our opposite side, delta S is our hypotenuse. And so we would use sine. Sine of our angle, 11 degrees, is equal to opposite, which is H, over hypotenuse, which is delta S. And if we cross multiply, we get delta S sine 11 is equal to H, because there's a 1 under here, so we're cross multiplying. So if we solve for, let's say, H, we've already solved for it. H is equal to delta S sine 11. So this H final over here, we can replace it with delta S times sine 11. And that way, we'll have a delta S here that we're trying to solve for, and a delta S here that we're solving for. And that's what the question's asking for. If the question was asking for the height, then instead, we would solve for the delta S over here. So we'd say delta S is equal to H over sine 11. And we would replace this delta S over here with H over sine 11. And then we'd have an H over here and an H over here. They're both the same thing, so they would both be an H final. And then we would solve for that. Okay, but in this case, we're not trying to find H final. We're trying to find how far does the block travel up the incline. So that means delta S. So along the incline, what distance does it travel? Okay, so we're not solving for H, we're solving for delta S. So I'm going to keep delta S in my first equation here for work, and I'm going to replace H final in my UGF equation with delta S sine 11. So I'll just rewrite everything right now. So I have 1/2 mv initial squared plus fk delta S cos beta equals mg and then delta S sine 11 degrees. Okay, so I'm trying to solve for this delta S. So I'm going to bring everything to one side of my equation and solve for it. Before I do that though, I'm going to figure out what my Fk is, because I haven't done that yet. So now remember, Fk is the force of kinetic friction, but it's while it's on the ramp, because the ramp is the only place where there is friction, as it said in the question. So if I were to draw a free body diagram of my block on the ramp, anywhere on the ramp, I would have a force of gravity, which equals mg, and they don't tell you what the mass is, so I'm just going to say it equals 9.81 times the mass. I would have a normal force over here, and I'd be able to figure out what my normal force is by decomposing my force of gravity. So this is 11 degrees here, and so my adjacent side here would be 9.81 m cos of 11 degrees. And that means my normal force is also 9.81 m cos 11 degrees, because those two forces have to be equal but opposite to each other, since the net force in the y direction is equal to 0. Okay, so now what other force do we have? We have the force of friction. And force of friction opposes the motion. The block is moving along the horizontal frictionless surface and then up the incline, so friction would be pointing down the incline then. So this is my force of kinetic friction. And how do we calculate it? The force of kinetic friction equals the coefficient of friction times the normal force. So I'll write that on the side. Force of kinetic friction equals the coefficient of kinetic friction times the normal force. The coefficient of kinetic friction is given 0.260 times the normal force, which we said was 9.81 m cos 11 degrees. So I'll just calculate this so that we have a value. So it's 0.260 times 9.81 cos 11. We get 2.5037, but there's still an m here, so I'm just going to write m next to it. Okay, so this is my force of kinetic friction. All right, so we know that value. What about this beta over here? Beta is the angle between my force of kinetic friction and my displacement, and my displacement is going up the ramp. So the angle between those two is 180 degrees. So that's what goes in for beta. Whenever we're doing work done by friction, the beta will always be 180 degrees. And cos of 180 degrees equals -1. So my equation just ends up being minus Fk, which in this case is 2.5037 delta S, and my delta S, I said I'm leaving it as delta S because that's what I'm trying to solve for, and my cos of beta was -1. That's where this minus came from. Okay, so I'll rewrite everything. I have 1/2, my mass we don't know, my V initial was 5.7 squared, so minus 2.5037 delta S equals my mass, which I still don't know. Oh, and I think I forgot my m. Yeah, so I had an m over here. Minus 2.5037 m delta S is what I'm solving for, equals m times 9.81 times delta S times sine of 11 degrees. So I'm solving for the delta S that's here and here. Okay, so I'm going to bring everything with delta S onto one side, and I'll type out this 9.81 times sine 11 to see what I get. 9.81 sine 11 gives me 1.87183. Okay, so I'm going to bring that all to one side. So this over here is just 1.87184. There's still an m, so I'll put m next to it. Then I'll bring this term to the other side of the equal sign, so it'll be plus 2.5037m. Oh, and I'm missing my delta S in both of them, so this one should say delta S plus 2.5037m delta S. And on the left, I'll just keep my 0.5 times 5.7 squared. And I get 16.245 m. Okay, so that's what my equation looks like right now. I could factor out an m everywhere, and then they all cancel out. So this m, and this m all go away. On the right side, I could factor out a delta S, or I can just add these two terms together. Let's just do that. So I have 1.87184 plus 2.5037, and that gives me 4.37554 delta S is equal to 16.245. Now I can divide both sides by 4.37554, and I get delta S is equal to 16.245 divided by 4.37554, and I get 3.71, or 72, sorry, 71 actually, and then that's meters. So I solve for my delta S here. Okay, so the question's getting trickier and trickier. Okay, so that's question 4. Let's move on to question 5. A 5 kilogram box slides down a 5 meter high frictionless hill. So I'll draw it like this. Here's my box. It's sliding down this hill, so it's 5 meters high. So that's the height of it. So that means this over here. This height right here, my initial height is 5 meters. Then, and it starts from rest, so that's my V initial is rest. So that would be 0 meters per second. So it's a box, it slides down the hill, then it goes across a 2 meter wide horizontal surface. So this is 2 meters long here. And then it hits a horizontal spring. So here's a spring here. With a spring constant, so this is the K value, is 500 newtons per meter. The other end of the spring is anchored against a wall, so this is my wall over here. The ground under the spring is frictionless, but the 2 meter wide horizontal surface is rough, so over here, this is rough. And the coefficient of kinetic friction of the box on this surface, the rough surface, is 0.25. So this is the coefficient of kinetic friction, is 0.25. How far is the spring compressed? So we're looking for that delta X of the spring. Okay, so that's what we're trying to find. So let's start with our energy work equation. So the total energy initial plus the work done is equal to the total energy final. So now what kind of energies do we have? Initially, we have no kinetic energy because it's not moving. The speed is 0 or it's at rest. So I'm not even going to put that in. We have gravitational potential energy because it does have a height of 5 meters there. So UG initial. Actually, I'll put all of them in just so we can see. So EK initial, there is a spring in the question, so I'll put in elastic potential initial. Plus the work done. The only external force acting on the system is friction here. So we have a work done by friction is equal to all the energies at the end. EK final plus elastic potential final. Okay, so now let's go through all of them and decide which ones are 0. So initially, we don't have a velocity, so that means that EK initial is 0. Initially, when our box is up at the top of the ramp, our spring is not stretched or compressed. So that means that the delta X up here is 0. So that's the initial delta X is 0. That means it's at its equilibrium position. It's not stretched or compressed. So then that means that the UE initial is 0. At the end, the box compresses the spring. It's at its minimum. The spring gets compressed, but the box is no longer moving because it's slowing down as it compresses the spring. Once it comes to a stop, the spring is compressed to its max amount. So that means the EK final is 0. It's also at the bottom here where the height final is 0. So the UG final is 0. Okay, but the spring is compressed, so that means that there is an elastic potential energy. Okay, so now we can start to put in our formulas. So UG initial is mgh initial. Work done by friction, okay, is the force of friction, so kinetic friction, times the displacement, times cos of the angle between the force of friction and the displacement, is equal to the elastic potential final, which is 1/2 K delta X squared. All right, so we're solving for how far is this spring compressed. We're solving for this delta X. Okay, so let's look at Fk and cos beta a bit. So Fk, we know, is the force of kinetic friction when the object is on this rough surface where there is friction. So if we were to draw a free body diagram here, what would we see? We'd have force of gravity, which equals mg, and we'd have a force of friction. force of kinetic friction. And now because the object's not moving or accelerating in the y direction, there can't be a net force in the y direction, which means the force of gravity and the force of kinetic friction should be canceled out. So the force of kinetic friction would also be mg then. We know the mass of the box is 5 kilograms. We know g is 9.81. So we know the force of, oh, I wrote kinetic friction. This should be the normal force here. So the normal force would be mg. Now the force of friction. So the object is moving to the right, so the force of kinetic friction would point to the left. So the force of kinetic friction is the coefficient of kinetic friction times the normal force, which is mg. Okay, so that's what's going over here, mu k times mg. Now what about the beta? So the force of kinetic friction is moving to the left. Which way is the ball actually, or the box actually moving? It's moving to the right. And so what is the angle between the displacement, which is this delta S over here, and the force of friction? The angle between the two is 180 degrees. Okay, so that's what the beta is. And the beta for friction is always 180 degrees in every question. So this is 180 degrees. And cos of 180 degrees is just -1. So this whole thing just becomes -1. So I'm just going to rewrite everything. mgh initial. I'm going to change this plus to be a minus now because of the -1. Fk is mu k mg, and then there's the delta S still, equals 1/2 k delta x squared. We're solving for this delta x here, so I'll times everything by 2, and I'll divide everything by k, and then I'll square root everything. So I get delta x is equal to 2 mgh initial over k minus 2 mu k mg delta s over k, all in a big square root sign. And now I'm ready to sub everything in. So I have 2, my mass of my box is 5 kilograms, g is 9.81, and the initial height was 5 meters, over k. They told me that the k was 500, minus 2 times the coefficient, which is 0.25, times the mass again, which was 5 kilograms, times gravity is 9.81. Delta S is the distance traveled while undergoing friction, so while there's a force of friction acting. So that's this distance right here. So this is my displacement, is 2 meters. So my delta S is 2 over my k, still 500, all in a big square root sign. So I will type that in. And I have 2 times 5 times 9.81 times 5 over 500 minus 2 times 0.25 times 5 times 9.81 times 2 over 500, all in a square root sign. I get 0.9396, which is 940 if I was to round it, and that would be meters. So it asks how far did my spring get compressed, and I would say it gets compressed 0.940 meters. Okay, there's one more question, question 6, but you'll see that there's a solution that's already posted. So you can try this one on your own. It's quite challenging because this block over here, it travels up the ramp and then it becomes this projectile. So you have to set this up as a projectile motion problem once it gets to the top. So you're trying to find the V final up here. And then in the projectile motion problem, that becomes your V initial. And then you would figure out how far it travels when it lands back onto that surface. Okay, so give it a shot, and there's a solution that's posted for you already. All right, thanks so much for watching. See you next time. Bye.